It's time to move on to the second half of the Kennedy brothers. That's just to make, I don't, as far as I know, there's no relation between the two. So Robert Kennedy and Eric Hughes are going to talk to us now about interstellar mission capability.
Hi, good morning. So this will be the completely anti-abstract. So I went through this exercise starting a few years ago because I wondered, people talk about going to other stars, and I thought, what mission rate might that actually be, just based on stuff we know about? So I looked at the methods of getting there. So I'll share my screen and just go through these slides super quick. Hang on, share. There it is. Okay. We'll keep it in edit mode so I can also see you. So what would it be? I've distributed the papers last night. One of the papers is about, well, why would we go? These are some destinations we would go. Finding a terrestrial world in the Goldilocks zone is certainly a good reason for going. The SETI paper illustrates another reason for going, which is to talk to others, because the idea of exchanging symbolic representations by radio just doesn't hold up. We don't even understand cultures 4,000 or 5,000 years old. They're like the Indus Valley civilization, completely undeciphered, unknown script, and they're us. That's only a few millennia old. So the idea of understanding what an alien is saying without actually being there in real time, interacting with their physical embodiment of intelligence is hopeless. So that'd be a good reason to go. How would you go? There are a number of ways. You've heard of breakthrough starshot. So that's going to be flinging small objects pushed by powerful laser maser beams. Here's one, a 3D print of one, which is in the bottom right corner. This is Project Dragonfly. This weighs about as much as a small car. Then there are self-propelled robots, about the mass of an aircraft carrier, size and mass of an aircraft carrier, but still machines, not big enough to carry a life system. And then there's world ships, which we probably won't see for a millennia. We'll have these will be based on asteroid colonies, billion tons or more. So it's these in-between machines that we are likely to get to our nearest neighbors within the next few centuries. I just don't see any other way based on engineering physics that we know about. So I go through the fusion reactions and came up with the surprising result. Stellar missions is boron, and you can replay my presentation to see why that's true, but surprisingly, it's humble boron, which it turns out is not all that humble because there's almost no boron in the cosmos. It's very, very rare. It wasn't made in the Big Bang, and it's not made in stellar nucleosynthesis either when stars blow up. It's only made by spallation of carbon, oxygen, nitrogen in the ISM by really, really high energy galactic cosmic rays. So where does boron fit in? It's a very rare substance. Now, can we make boron? Well, we can make anything. We made tritium in the Cold War, but it was $250,000 a gram. We make today, this is a transplutonium production rod, which I designed almost 30 years ago. And this here transmutes plutonium into gram quantities of californium, which is at the opposite end of the periodic table. And DOE sells californium for $25 million a gram. So it's not impossible to make elements that you desire, but it's really super expensive, and you're not going to be fueling starships with them, which need tens of thousands of tons of these elements. Boron is special because the reaction of it with a proton, fast proton, produces no neutrons. That's what you need for interstellar flight. And as to why, watch the video. So boron. So where is the boron? Surprisingly, it's here. And it's only here because Earth has tectonic activity, plate tectonics, and a hydrologic cycle, which none of the other terrestrial worlds do. Obviously, the gas giants don't. Perhaps some asteroids or moons like Io and Europa, which also have hydrothermal activity, maybe they'll have a means of concentrating boron. We don't know until we go there. Right now, all the boron we know about is right here. And so there isn't a lot of boron. Here's the surprise. The kind that fuses that you use for fusion fuel, we've got a gigaton of it, about a quarter of that on land, 3/4 dissolved in the ocean. If we ever start getting deuterium out of the ocean, we will definitely want to get the boron and lithium out of there too. So, and here's the global distribution of lithium, which is even less. And I'm not going to talk about it more because there's less of it. It's really rare. It's really hard to do the mass separation. And actually, the reaction is anemic. So boron is it. And that's it. We have 1 billion tons of boron of the fusible isotope. And that's it in the entire solar system. That's all the human race will ever have. So using those large stars, not the world ships, but the large machines, size of aircraft carriers, how many of those could we run? And the answer is 30,000 for the rest of time. That's our allocation of getting from here to even the nearest stars is 30,000. That's it. So the whole idea of, Star Trek, Starfleet, millions of ships, Star Wars, millions of ships zipping all over the place. No, it's on the order of tens of thousands of missions. So boron is the best fuel for that. So how do we reserve, since there's so few possible missions, how do we hang on to our boron and not do stupid stuff with it, like make laundry detergent out of it? Although the good thing about laundry detergent is when you use it, it dissolves, goes down a river into an ocean, and one day we may be able to recover it from the ocean. But if you burn boron in a power reactor to make electricity, it's gone forever. And boron is not made in our sun. It's not in the solar wind, so we're not going to get more of it. So we really need to preserve the boron, and I claim the way to preserve our boron is develop the deuterium cycle first. So we're not tempted to use the boron cycle to generate electricity. There is an example from the past, whale oil versus rock oil. Lighting homes at night, lighting schools at night was a really important thing to do 200 years ago. It's still important in the developing world. So it's something people did. We hunted whales almost to extinction because the other means of illumination were either very expensive or crappy. But we almost wiped out the whales. Luckily, the Civil War came along and saved the whales because the Confederacy sank all of the Yankee whaling ships just about in the Pacific. And luckily, here's this picture, which thanks to not William Alba, the speaker on the first day, who found this wonderful picture of Abraham Lincoln standing in front of the first oil well ever drilled. So rock oil came along to save the whales. And there's another example from the past, 4,000 years ago, of tin. And so the city-states of the past, 4,000 years ago, contended over just 3 sources of tin. And I think boron might be like that. It's interesting that another speaker mentioned Westphalian states today. So we may be contending over boron in the centuries in the future, if it's not a one world government, if we're still Westphalian nation states because of the highly unequal distribution of boron. So at that point, I'll say we have to protect the boron by developing the deuterium cycle first, so that the limited supply of boron is available for truly important missions of interstellar range. And also a complete conjecture, if we ever do encounter or detect a really big ship, a world ship, which is running on boron, which we can tell from the radiation emissions, we will know a couple of things. They're either incredibly rich or they're really, really desperate, or both. And now we will take questions, and perhaps if we have time, we will explain this photograph on the last slide. And I'd like to introduce my co-author and colleague whom I've been working with for 30 years, Eric Hughes. I do geoengineering with him and interstellar stuff with him and network security with him, all kinds of stuff with Eric. So thank you.
Okay, Ryan.
Yeah, thank you.
6 minutes instead of 5.
Thank you. This is fascinating stuff. So I've done some work recently on boron as well. So boron also has application in boron nitride nanotubes, which have similar properties as things we think of like carbon nanotubes and such. And there's been some supposition that you could use boron as a shielding element for radiation in starships as well. So there might be a competing use of boron in any type of interstellar mission, because boron-10 helps to shield from neutron radiation, from what I understand. But the other thing, so I just wanted to throw that out there. But the other thing,
let me jump in. Boron-10 converts to boron-11 under neutron irradiation and turns it into fuel. So there's not actually you're actually creating fuel out of the shielding element.
Oh, okay. So you could like shield the ship, then cannibalize your shielding as fuel, and just pray you have a thick enough layer.
Basically, that would be the. Although you'd have to run numbers to see if that's plausible.
Cool. And the other thing is, I just wanted to throw this out there. So I've done some, as a theoretical chemist, I've done some calculations recently, and boron actually makes some of the strongest chemical bonds on the periodic table. So if you bond boron to fluorine, it bonds like twice as strong as carbon does to itself. And so,
because it's so small, it's such a small nucleus. So the charge is really packed into a small volume, like lithium. Lithium makes very strong bonds.
Ryan, I think even more important is that boron will tend to form polymers. Like the structure of borates is incredibly polymeric and not a simple crystal. And so if boron weren't so rare, it would be a possible substitute for carbon as a combinatorial skeleton for chemical life.
Absolutely, because they've made boron like boron diamonds or boron fullerenes and some of those other things that go along with it. Cool. All right. Well, thanks.
Okay,
you're welcome.
Abhik?
Uh-oh, he's got audio trouble again.
I think
this time he's muted.
All right, so William.
Yes. So I actually have a couple of questions about this concept of we should not waste boron because it's elementally unique, which I get. But what I don't know is how rapidly are we using it right now? Should we be worried about this?
There's two kinds of use. There's chemical use and nuclear use. And so we're far more concerned with the nuclear use of it, which transmutes the boron into something else, rather than the chemical use, which turns it into a waste stream, which could be re-extracted from seawater later.
So, but in 2020, how rapidly are we using down this reserve?
About 1% a year.
Okay, so it's a somewhat
1% of our patrimony. So we use 10-ish million tons, on the order of 10 million tons a year. The reserves on land are 300 million tons. So we're going to go through the known land reserves in 30 years.
Okay. All right. So it is a valid concern from that perspective. The second question I have is admittedly more speculative, but it does relate to the two examples that you gave of
Hey, this
whale
is
oil,
SSoCIA.
right, and of tin and its use in bronze. So we're no longer concerned about whale oil, as you said, but that's because we found an alternative, right? We found rock oil, petroleum, and similarly, we left the Bronze Age, right? And we started using iron ore. So again, this is speculative, but should we really be concerned about boron and have a strategic national reserve as we do for helium and other things, and for petroleum, actually, for that matter, if potentially down the line we'll find something else?
Well, I would rather, if we don't, that's kind of betting on the come. So I would rather, we discussed the tragedy of the commons yesterday and the day before. There were speakers on that. So this isn't just a national resource, not a strategic national resource. It's a resource for the human race. And
I suppose
it's a patrimony.
No, I
So-
agree that the argument follows. I just suppose I wish that the two examples that you had given were not examples where then technology saved the day and alternatives were presented. I think the case would have been stronger if we ran out of something and then we didn't find an alternative.
So I did preface the title of the slides, the ones that showed all the nuclear reactions, light reactions that we know about. So maybe there's another light reaction that we don't know about, undiscovered, that is aneutronic, which is a necessity for interstellar flight, because you can't be throwing away 3/4 of your energy in a fast neutron, which go out isotropically. They have no charge, so you can't stop them. They don't create thrust because they're isotropic. So you can't be, because the rocket equation, all the important stuff is in the exponent. So the reactions have to be aneutronic, and there ain't that many aneutronic fuels.
Yeah,
Maybe we'll discover some more aneutronic cycles. Be a really good idea to look into that.
I totally get
The theory suggests.
I missed the end there.
Sorry, Dr. Alba.
But I guess I froze.
Robert,
it's my fault then. I'm sorry.
No, Robert's internet where he lives in Tennessee can sometimes be flaky. I've had experience with that.
Oh, okay. All right. Well, I mean, I totally get the scientific, the chemical argument, right? The nuclear chemistry argument, and I'm following along on that. I guess I'm just saying rhetorically, if you wish to convince others of this, that the cases you ought to present ought to be cases in which the further technological developments did not pull us out of the problems that we thought we might anticipate.
That is why I'm hanging out with a bunch of sociologists and astrobiologists right now. Because there are a few examples from the past where technology saved the day, but
you can't count on them.
All right, Carlos,
yes.
Time for a quick question.
Okay, I'll try and pare down my question then. So I'm interested in the potential future uneven distribution of boron reserves, as you pointed out with your maps. At what rate are we, through extraction, redistributing the supply of boron such that in the relatively near future, it's not going to be the fact that it's all in California and the Salade de Uyuni and stuff like that, and we'll just have to get our boron back from evaporation mining and melting down Pyrex?
So it's 30-ish years.
Okay.
So not, it's not millennia off. It's a generation off.
If anybody wants,
so this is really urgent then.
If anybody wants to measure peak boron, there's probably a research project there.
All right, so I think it's probably time to end this session here.